For these notes on linear functions, you can either handwrite these on the next page in your spiral, or you can take the pieces of paper that I gave you and tape or glue it down, and then just fill in as we go. Linear functions. So if you want to identify a linear function from a graph, a linear function is a function whose graph forms a straight line. It's linear because it has a line, and it is a function because none of the x values repeat. Two components must be fulfilled. It must be linear, and it must be a function. So I gave you a strip of paper. There are 7 graphs, and what I'd like you to do is just cut them out and put them on the examples and the non-examples. So the first one is a line that goes through the origin. It's a diagonal line. It's going up from left to right. It is linear, and it is a function because none of the x values repeat, and if you were to do the vertical line test, it would pass. So I'm just going to sketch this out. This would be the first one. It looks like this, kind of like that. The second one is a set of parallel lines. The third one is a line that is going down from left to right. The fourth one is the absolute value graph. Then there's a fifth one that has a curve, sixth one has a curve, and the seventh one is a line. So let's see what you think. You can stop the recording, or you can just tape them in later. This is what your page should look like. The first one is the absolute value function. It is not linear. The next two are curves, and the last one is a vertical line, and while it is linear, it is not a function because it doesn't pass the vertical line test. So this is how you would identify linear functions from a graph. If you wanted to identify linear functions from a table, what you want to do is you want to look for a common difference between both x and y values. So let's take a look here. So here we're going plus 1, plus 1, plus 1. They're all plus 1s. And here it is -3. So we have a common difference of as the x values go up by 1, the y values decrease by 3. Let's take a look at the second one. So here we also are going up 1. And then on this side, we are going down 3, down 1, up 1, up 3. So while there is a pattern that's happening, it's not a common difference. It's not the same. We're going down 3, down 1, then up 1, up 3. So the second one is not a linear function. Another way that you can determine a linear function is if it is written in standard form. So standard form is if it's written in ax plus by equals c. If it can be written in this form, it doesn't have to be in that form right away, but if it can be written in that form, then it's going to be linear. So taking a look on the left-hand side, here are some examples. 3x plus 2y is 10. And if you notice, you have the a is the coefficient of 3, there's your x, the b is the coefficient of 2, there's your y, and the c is the constant. That is in standard form. The second one is y minus 2 equals 3x. It's not ax plus by equals c, but we can put it in that form by moving the 2 to this side, and then subtracting the 3x. And you would end up having -3x plus y equals 2. So you do have it in ax plus by equals c. And the value of the b in this case is that 1. Negative y equals 5x. We can go ahead and subtract 5x, and we have negative 5x minus y equals 0. So we have ax, there's your by, and there's your c. So these are all linear. On the right-hand side, these are nonlinear. 3xy plus x equals 1, x cubed plus y equals negative 1, and x plus 6 divided by y equals 12. So what are some key observations that you might notice that might make something linear versus nonlinear? You can jot a couple ideas down right here, and we will talk about it tomorrow. Pay careful attention to this one. Anybody have any questions on why that's nonlinear? Down here we have a career application. We have Spencer is selling handcrafted hockey stick carriers for $5. The amount he earns is modeled by the function f of x equals 5x, where x is the number of stick carriers he sells. Yes, this should be f of x. Graph this function and give its domain and range. So Spencer could sell none, and he will earn none. He could sell 1, and he would earn 5. He could sell 2 and earn 10, 3 and earn 15, 4 and earn 20, 5 and earn 25. And you could graph these. We'll just give a rough estimate here. So 0, 1. Okay. And you can see that we are creating a constant increase. We do have a common difference on both sides. The domain and the range. In this case, your domain 0, 1, 2, 3, 4, 5, ... And your range 0, 5, 10, 15, 20, ... Are we connecting the dots here? We are not connecting the dots. Can we say x is greater than 0, y is greater than 0? We cannot, because these are whole numbers. When they're whole numbers, we can't have a greater than. We can't do the range of values. If you wanted to put it in set theory notation, you could say x such that x is an element of whole numbers, x is greater than 0, if you wanted to do that. Otherwise, this is okay as is. So you might need to do 2 pieces of paper for your notes, or you could put them all on one. It's up to you. We'll go over the rest of this tomorrow and do some practice in class.